Thanks for the invitation. It's great to be here in person. I have to say I was a little bit nervous because the last 3 times I was supposed to come to Paris, I had to cancel basically with 24-hour notice. Okay, 2 of those were in March 2020, so it was a tricky time. But I was wondering what would go wrong this time. And okay, it's great that I could be here and do this talk in person. So today I'll tell you about, the talk's not really going to be based on one paper, but more about a series of paper and some ongoing work that we've been doing together with Jan de Boer in Amsterdam, but also Pranjal Nayak and Julian Sonner, who are at the University of Geneva, Diego Liska, who's an excellent grad student in Amsterdam, and Tarek Enus, who's a postdoc in Amsterdam. And the talk today is really going to be about quantum chaos, and more specifically chaos in conformal field theories. But really what got us into this in the first place is holography. So I really wanted to start with a few words about holography, and well, both for the room and the people online, tell me if I write too small. I'll try to write big enough. I can't do much about my handwriting, but I'll try. So you know, ADS-CFT is a duality between certain conformal field theories and theories of quantum gravity in anti-de Sitter space. And really, the left-hand side of the duality here is a complicated system. You know, it's a large N, strongly coupled conformal field theory. So it's complicated, but you know, the rules of the game are known. It's a quantum field theory. Hopefully one day the bootstrap will just solve this for us, or maybe the lattice will solve this for us. So it's difficult, but we know what the rules of the game are, and we know what we're supposed to do, at least in principle. The right-hand side, I would say, is much more complicated because we don't even know really what this is, what quantum gravity is non-perturbatively. So here, I would say that this is even more complicated because, you know, the rules are unknown. But even though this is in some sense more complicated, it does admit a description, or at least at low energies, in terms of an effective field theory, which is, you know, say the Einstein-Hilbert action here, and this is simple. Okay, so you know, in some sense, the right-hand side is both more complicated because, you know, the fundamental and non-perturbative rules, we don't know what they are. But if you look at low energies, then the theory admits, you know, an effective field theory description in terms of something that's simple. Okay, this is just, you know, semi-classical Einstein gravity. And so, okay, we've used this for a lot of things. And one thing that we would, you know, really eventually like to understand is, you know, what is the spectrum of, say, n equals to 4 super Yang-Mills at strong coupling? Okay, we don't know what that spectrum is, but, you know, you should think about it as something very complicated. Think about like a barcode with really complicated and finely grained spectrum. Say, if you look at, you know, states of energy n squared. And one thing that we would like to do eventually is you know, understand what the spectrum is, solve for the spectrum of n equals to 4 super Yang-Mills. And of course, currently we don't know how to do that, but the problem is even harder if I just tell you, okay, forget about the individual eigenvalues of the Hamiltonian, let's just try to count the number of states. How many states are there in some energy bands? We can call this, you know, e to the s. And even this we don't know how to do. Just getting a rough estimate for how many states there are in a given band, we don't know how to do, you know, in n equals to 4 at strong coupling. And, you know, to solve the theory, we don't want to just talk about the spectrum of the Hamiltonian. We also want to talk about correlation functions. And so, you know, one of the fundamental quantities that we would like to compute is, say, the matrix elements of certain operators in energy eigenstates. And I'll describe this in a lot more detail in a couple of minutes, but this structure is expected to have a universal form given by what's called the ETH ansatz. And for now, the details of it are not too important, but what's important is that it has a sort of universal structure in terms of a diagonal piece. it has a universal structure. There's a diagonal piece, which is large and given by a smooth function of the average energy here, and an off-diagonal piece, which is exponentially small in the entropy, and with another smooth function of both this time the mean energy and the energy difference here. Okay, and this is known as the ETH ansatz. And again, bear with me because I'll tell you all about it in glory detail in this talk. But this is, supposed to have a universal structure. And one thing that we'd like to solve also in n equals to 4 is, the value of these matrix elements exactly set to solve the theory. But again, we don't know how to do this. And maybe what I could just write down is that, the type of observables that like to calculate that probe either this or that here would be, say, the finite temperature partition function. And here would be correlation functions at finite temperature, maybe 1 and 2 point functions. Okay, so these are the things that we would really like to understand in n equals to 4 super Millset strong coupling, and we don't know how to do that. Well, in general, to really solve the theory, we should probably allow O to be anything. Here, let's just say for now, O is a simple operator, but these are high energy states. Okay, thanks. That is going to be a large part of what I'll talk about today. Short answer is not quite, but there is something else that we think replaces it. Okay, so these are the types of things that we'd like to solve, and we don't know how to do it. But here's where gravity is useful, and where the duality is useful. Is that on the right-hand side we have in principle a theory of quantum gravity, but at low energies it's well approximated by general relativity, and what you can do is just consider boundary conditions that correspond to finite temperature in the dual CFT, and look for solutions to the equations of motions. Those are just solutions of GR with semi-periodicity and Euclidean time. And those solutions are known. It's just a Schwarzschild black hole in ADS. It's a solution that looks like this. And then Bekenstein Hawking told us many years ago that the entropy of the black hole is given by the area of the horizon over 4 g newtons. And the way you should think about what this is computing, so this is really a function of the radius of the horizon, but you can re-express it in terms of the mass of the black hole. And so really what this is giving you is it's giving you access to this function here. This function that you don't know how to compute for first principles in n equals to 4, but you can compute it in the dual theory in gravity, and it tells you, it gives you an estimate of how many states there are in a given energy band. Okay, and once we have this solution, we can consider not just the on-shell action of the solution, but we can also start, probing the solution with correlators. So we can compute a 2-point function on the black hole background, say, or in principle a 1-point function on the black hole backgrounds. And so these are quantities that we can compute. And in terms of the ETH ansatz, what you should think about what these things are computing for you is it's giving you so you can compute these functions here, and these give you access to these smooth functions here. Okay, again, I'll tell you more about ETH in a second, but as I said, the only thing that's important is that there's some large diagonal piece and small off diagonal piece with some smooth functions that are theory dependent and that are not known in general. And we don't know how to compute them from first principles, but we can use gravity to do it. Okay? This may not be surprising to you. You might think about this as just black hole thermodynamics, which it is. This is just black hole thermodynamics, but it's just black hole thermodynamics, but it's already very powerful. It's giving you access to some functions that we have no idea how to compute from first principles in the field theory. Okay, and maybe I should say that this is more than what you would think. Then this is more than an ordinary EFT would be.
Well, we have a question from Francesco Nitti, who is asking, how do you compute matrix element between two different states in this picture?
Oh, we don't. So the matrix elements is the microscopic data. What I'm saying is that matrix elements have a universal structure with, there's some sort of crazy, I'll get to this in a second, but there's some crazy random oscillations that we don't know how to control in gravity either. But the things that we do know how to calculate in gravity are these smooth functions that multiply. So we don't calculate this exactly. In the same sense as we don't calculate the exact energy levels using gravity. What we do is we calculate the average number of states in a given energy band. Does that?
Yeah, here.
Okay.
Can you zoom out a little bit? Zoom out.
Yes, question. Yeah.
So are we supposed to think of basically answers as holding in some order in G Newton? Like, because you're saying that we can calculate these new functions by some.
Yeah, not really. In principle, nothing prevents you from, doing all kinds of loops to this function, and that'll just give you the G Newton expansion of this smooth function. So, in principle, at least for any finite order in loops, we think that this is something, okay, it might be hard to actually do this in practice, in gravity, but we think that in principle, we could have access to this. What's important is that the entropy is not perturbative in G Newton, it's exponential in G Newton, and that's what's being kept track of.
Right. So what are a bit the most basic assumptions that go into this ETH?
I'll get to that. I didn't want to dive in too deep. I just wanted to sort of give a picture of what gravity has. I'll tell you all about ETH and what it applies and so on and so forth. Okay. And yeah, the comment I wanted to make is this is more than what you would call an ordinary effective field theory. What you might have called an ordinary effective field theory is something where you take this action, expand it around the ADS background, and use that to compute correlation functions to some order. That's like perturbative scattering amplitudes in ADS around the ADS vacuum. This is very different because this is a non-linear solution to Einstein's equation, but it's still semi-classical. Curvatures are small everywhere, so we think this gives a good approximation to what we're calculating. But it's already sort of hinting that gravity is maybe more than an ordinary effective field theory. It certainly seems to be more powerful than being able to compute things below some cutoff. If we thought that an ordinary effective field theory computes all processes, or maybe I should put an energy here, they're really the same in CFTs, but that that accurately computes all processes with some energy smaller than a cutoff energy. This is beyond that. Because this cutoff energy here we would take to be much larger than the ADS scale, but much smaller than the ADS scale, but much larger than the Planck scale. And this is the energies here in these black holes, they're Planckian. So it goes beyond something like that. Okay, yes.
In addition to gravity being able to compute those functions f and g for you,
yeah.
It should also tell you that the ETH ansatz holds. So in particular, if it's true in the CFT, gravity should tell you that, and you should be able to derive the e to the minus s over 2, for example, and just note that these two effects come at different parametric orders, not just to use it as a computer of those two functions, right?
Well, I'm not completely sure. Well, okay, this comes back to maybe Miguel's question about when the ETH ansatz applies and how do you know that it applies, and there's no proof of it, so it's something that you have to assume, I would say. And there's a lot of, I'll get to that a bit later, there's a lot of evidence from numerical calculations that you can do in, say, in quantum mechanics. But I would say it's the second thing that you said is that we think there's something of this type that applies with smooth functions that are theory dependent and operator dependent. That we don't know, and gravity is a tool to compute them. Whether or not gravity can test if this structure is true or not, I guess is part of the point of the talk today, but I would say at this stage, let's assume that this ansatz is true, and then gravity is a tool to compute this. So it's like it's a tool to compute this.
It really depends what you assume about our limit. I mean, at this point, you can always write.
Yes, exactly. It's all about
so,
yes.
I mean, you're just using it at the level what's out and squared.
Exactly.
In some sense, and
yes.
Okay, but when you try and compute other stuff like higher moments of
yes, I'll get to all of it. This is what the talk will be about, essentially. Absolutely. So maybe I can slightly hold off, and then we can get back to that in a second. Great. Okay, but so you know, this has been known for essentially since the beginning of ADS-CFT, maybe even if it wasn't written in this language. So we've known all of this for a long time, but I think what we also, you know, would have said all the way up until maybe 2 years ago, is that this is what we have access to all these smooth functions, but that's it. That's it. You know, we will never know anything more about the individual black hole energy levels, the black hole microstates, and we will never know about the RMN. So, you know, we would have said that, you know, more details about this stuff, that this is beyond reach. That is already really surprising that we're capable of calculating these smooth functions, but that's it. That's where it stops. Okay, there's no free lunch. But progress in the last, say, 2 or 3 years have actually shown us that gravity knows a lot more. And this has really, the new insight is that gravity seems to know a lot more. And indeed, it seems to know about, you know, correlations of these energy levels, or of these elements RMN that I haven't said too much about yet. Okay, so this is the new insight. Okay, and the sort of prime example, the first thing that we realized is that you can define a quantity which is called the spectral form factor. Just the analytic continuation of the square of the partition function. And it's something that people that study random matrix theory care about a lot. And in quantum chaotic systems, this is supposed to have a universal form. It starts, you know, at some initial value at early times, and then due to these phase interferences, it starts decaying. Okay, and once you reach very late times and the signal is exponentially small in the entropy, it starts to have some crazy erratic oscillations. But sort of below these crazy erratic oscillations, there's a sort of universal behavior that appears, which is a linearly rising ramp and then a plateau. And this continues for a very, very, very long time. So this is time. This continues all the way until time, which are, you know, doubly exponential in entropy, where Poincare recurrences happen. And I guess, well, this is something that I've never understood actually. I was always taught in French that the Poincare's theorem is the théorème du retour de Poincare. So now in English we say the recurrence of Poincare. So anyway, but we're in this building, so I should say something about this. But okay, very, very late times. This is e to the s. Then there's another spike, and then this pattern repeats again. Okay, and what we've realized is that this ramp here. This ramp is related to the long-range energy repulsion of the eigenvalues of the Hamiltonian, and this ramp can be accounted for by gravity. If you take into account a solution that looks like this, so this is a cartoon of gravity here. There's 2 CFT circles corresponding to these 2 temperatures here. So, you know, this is like beta 1 that we're going to evaluate at beta plus IT, and this is beta 2 that we're going to evaluate at beta minus IT. And if you look at the contribution of a wormhole like this in gravity, you reproduce this ramp. And like I said, this in some sense goes beyond our wildest dreams, because, you know, as I said, we didn't think that gravity could know any more than what it did about here, and it seems to know something about energy, you know, eigenvalue repulsion of the Hamiltonian. And that's really something that has to do with discreteness of the spectrum. So, you know, it's not seeing the eigenvalues, but it's you know, decoding some part of the correlations in this very complicated spectrum. Okay, and this is in some sense, well, I think certainly for me, if somebody had told me this, I don't know, 5 years ago, I would have said, no way, it's impossible gravity will ever know about this. But apparently it seems to.
So I mean, is this really specific to gravity? If you just have some QFT in ADS and you look at the boundary CFT, then can you build exactly the same quantity and don't you have to have the same physics?
Oh, yeah, no, you won't have the same physics at all, right? So if we take a QFT in ADS, well, first of all, if it's a free QFT in ADS, then the energy levels are extremely regular, right?
Yeah, no.
So way before you reach here, you know, you'll start to have some periodic oscillations, and even if you make it weakly interacting, you know, you'll never reach a structure like this because you'll never reach energy. So it's really important here that the mean energy difference is exponentially small in the entropy.
And you think a generic QFT does not have that?
A generic QFT in ADS will look nothing like this. The time scales, you know, if it's an interacting theory in ADS, it might have a similar feature, but at like much smaller times, and it's going to be sort of less. It may look something like this, and then you know that Poincare recurrence times is order 1, so it'll start again way before you reach down here.
So what's the time scale on this axis?
Yeah, so this is each less. Everything that's happening around here are time scales of order each less. Yes.
Should I understand this answer in terms of the fact that this beginning part of the whatever is wrong so deep is because there are additional gravitational saddles that contribute to whatever correlation functions or form factors that you're computing, which would not be happening for a QFT in time areas.
Yes, that's true. Yeah, exactly.
But if you have a QFT, it's also non-linear in terms of the field, so there will also be some classical solutions in terms of some field profile. I find this a bit surprising because the density of states for a non-local sense is larger than that for a gravitational theory.
So if you let it go on forever,
but it even has more states than this one. So how can this?
Yeah, but the spectrum is very regular, right? Even if you
Why?
Even if you allow 1/n corrections. You know, you're going to get basically the spectrum is going to look like a generalized free theory plus small corrections around that, right?
I don't know why.
It depends if the QFT is weakly interacting, and you want to make it strongly interacting.
Just a random QFT. This is all non-perturbative, right? So
yes.
The spectrum I think should look random, no?
Yes, but
QCD. Let's think of QCD.
QCD and ADS. Yeah. The problem is that you know I mean, this is really related to dynamical parts of gravity, and you know the fact that you have a very large entropy like this. So you know,
I mean, you're doing holography, so I mean, this is a different topology. We have to take on to the topic.
No, but they're also non-local. They're also non-linear solutions of field profiles.
Yeah, I mean, if you take a random field theory, it could have the same behavior, but I mean, like presumably there's going to be some there. So if you put it in complex case, but if you want to do a gravity computation of that, you need to go to 1 dimension higher, and then dynamical gravity and then well.
Yeah, you really need the new topology. I mean, you can do thermal physics, but if you do just take a strongly coupled QFT on thermal ADS, you'll see some form of something like this. But the time scales will be completely different. There's not really going to be a large. So if you turn the gravity off completely and then you take the thermodynamic limit in your system, you can attain a very large entropy, and then you will see a curve that looks like this.
It'd be larger, right?
Yeah, it could even be larger in principle. But that's sort of the.
And you have to see recurrences and all that.
Yeah, but you know, so
we can discuss this.
Yeah. I mean, this is very universal, and so it's why it's exciting is that any quantum mechanics system has a curve that looks like this. But we're trying to understand the curve, say in n equals to 4 super mills, that has a stress tensor and does have gravity. And so, so I think that's why we have to care about gravitational effects and non-perturbative status. Yes, there was another question.
No, it's okay.
Okay, yeah.
Well, why do you say you'd be surprised that gravity knows all about this? Shouldn't gravity know about all this?
Well, so I had here the right-hand side, which is the quantum, like the full non-perturbative quantum theory of gravity. Should in principle know about everything, about. But now we're not talking about the full theory, right? We're talking just about the low energy effective description. So it's kind of miraculous that low energy description captures some part of these very non-perturbative effects that have to do with discreteness. At least to me, it's very impressive somehow. So gravity is smarter than what we thought. I think that's kind of the message. Okay, and this is not unrelated to all this progress on the page curve. It's a different perspective, but it's very much connected.
Alex, in what dimension would you say this has actually been established?
Yeah, so
Be a little clear about this.
yeah, I should say something about that. This has been, say, carefully established in 0+1 dimensional quantum systems. So for quantum mechanics, it's been partially shown in 1+1. So for 2-dimensional CFTs, on the gravity side, this is some work by Kotler and Nipson. It depends if you want to think that constrained instantons are accurate description, but if you do, you get a picture like this. And beyond that, I'd say it becomes murkier. It hasn't been very carefully shown. And the problem is that these types of solutions are rare. Actually, even in JT gravity, this is not a true saddle. Here you get away with it because you can actually do the exact path integral, but so I think this is telling us how it's supposed to work. We haven't figured out all the details yet. Good, yes.
Also, I mean, is there not like a one-to-one correspondence between ramps in a quantum system and wormholes? Because I think in JT gravity and SYK there is, but for example, like in 3D, in an CFT, you have no ramp, but there should be wormholes anyway.
Yes, that's a good point. So the ramp will appear if the system is chaotic. For narrow CFTs, you're on the borderline case where say if you're at a rational value of the radius, they're not strictly speaking rational, but they're like the free boson s equals to 1. They're on the edge, and so they're not true. They're clearly not true chaotic theories, and that's why if you do the ensemble average over the narrow CFTs, it looks more like something like this. It does have a plateau at late times because each individual theory has a discrete spectrum. This is really related to the actual discreteness of the spectrum, but it doesn't have this intermediate linear ramp phase. So it's important that the theory is chaotic.
Yeah, but it does have wormholes. That's the
yes, but it's in a wormholes in a very weird theory of gravity. So yeah. Okay. So I don't know exactly what to make of that, but.
So is the definition of a chaotic quantum system one that follows this verb?
Say, with a linear ramp at some stage. Okay. It's not completely clear how to define quantum chaos rigorously, but we could take that as a definition. Yeah. Very good. I'm probably wildly running behind. Well, okay. Anyway, I didn't have a super fixed program, so we'll see how far I go. But there's a price to pay in this story. And the price to pay is known as the factorization puzzle. And actually, this is like, I don't know, 15 years older than this progress on the spectral form factor, because before we were actually confused about wormholes before realizing that they were useful and giving us something that we thought was supposed to be there. And so this is known as the factorization puzzle. And it was first explained by Miles and Malpasena. And the problem is that, say you want to compute this, so we're going to compute the product of partition functions in a CFT or in quantum mechanics. It doesn't matter too much. So, let's compute the product of partition function on disconnected spaces, which should clearly be just the product of partition functions. But now if you try to evaluate this in gravity, you're going to have two types of solutions. The first one, you're going to just sort of fill in smoothly the circle. So you're going to get something that looks like, that has a topology over this, that looks like this. But then if you include this wormhole contribution, you have a different topology that looks like this. And so the evaluation of this answer using gravity is just not the direct product of two functions of beta 1 and beta 2. You have some beta, it's going to be some, so this will be a function of beta 1 and beta 2 that doesn't factor. Okay, and this seems like a contradiction with what we know in the CFT, which is that it should be just the direct product of two functions. So people were really confused about this. They were trying to show that all wormholes should be unstable. And the more recent perspective is that, well, maybe that's okay if there's ensemble averaging happening in the CFT. So if you really think about CFTs labeled by some value of decoupling, and you do something like this, then there's no it's okay that this is, no longer a factorized function. Okay, and what I want to do today is give a different perspective. I don't think ensemble averaging is fundamental at all. I think it happened to be the case that like Eric was asking, this really works best in 0+1 dimensions. So for quantum mechanics, where the dual of JT gravity is a matrix model, or the SYK model also explicitly, involves averaging, but in n=4, there's no averaging or say, we could even take an M theory example where there's no averaging that you can do, say in the 2,0 theory. So I don't think averaging is fundamental, and I want to give a slightly different perspective based on quantum chaos. Okay. So that's sort of the plan for the rest of the talk is I want to first discuss what the ETH ansatz is in detail. There were already several questions about this, how it applies to conformal field theories, what it doesn't capture and why we need to go beyond, and then give a bit of interpretation of all of this in terms of gravity. Okay, so this was my very, very lengthy motivation, but are there any questions before I move on? I hope everything's still okay on the.
Yeah, well, I get the complaint and I try to resolve them.
So people are angry with you.
Now they are quiet, so I guess I'm not doing so bad.
Good. That doesn't mean they're happy. It just means that maybe they gave up.
Yeah, you have a question, Francesco? You just wrote question.
Yes, it's probably better if I say it. Can you hear me?
Yeah, I hear you. Yeah.
Yeah. Okay. Very good. So, are there an example in greater than 2 dimensions where both the two kinds of geometries that you sketch in the blackboard are allowed in the same theory?
Yeah. So that's a great question. What I would say is that we don't really know what the rules are. So from the gravity perspective, we don't know if we should be, summing over topologies or if we should restrict to a fixed one. For a long time, the picture was, that something's wrong with this, so we should, either not include it from some principles that we don't know, or show that it's unstable and hence it doesn't contribute.
No, but my question, I mean, the sense of my question is that in all the examples I can think of, you have either one or the other, even if you fix the two boundary conditions. So, for example, in order to have a wormhole geometry, say in ADS 5, you have to sort of have slice your spacetimes by anti de Sitter.
Oh, yeah.
And if in order to have a geometry that cuts off, you have to slice it by spheres. But you cannot have, in the examples that I have in mind, both topologies allowed at the same time.
Yeah. So yeah, very good. So I certainly know examples for 2D CFTs where both are allowed.
2D, okay. Yeah.
Yeah, and then in higher dimensions, sort of the state of the art is a paper by Marelf and Santos that came out, I don't know, earlier this year. And they looked at a whole plethora of wormholes where they have in principle both disconnected and connected pieces, and both are allowed. And what they did is studied the perturbative and non-perturbative instabilities of these solutions. What you're right about is that in higher dimensions, you need to do something to get a wormhole solution. So either you put negative curvature on the boundary, but that's typically bad for stability reasons, or you can turn on sources. And most of the geometries they consider, they have non-trivial sources here. And that's what allows to support a wormhole like this.
Okay, thanks.
Yeah, great question. Okay, so if there are no other questions, let me now give a review of ETH. So I guess we decided that our definition of quantum chaos is systems that have this linear ramp in the spectral forms factor. And what we believe is true is that in all such theories, there are universal properties. So this is maybe one of the most, the strongest universalities that we see in physics, is that in all of these theories, there should be a universal property, I guess I call it EN, for the matrix elements of simple operators. So now let me go through this in detail and say all the things that I didn't say earlier that we already asked about. Okay, so this is a matrix element of an operator. We're going to take O to be a simple operator. And in quantum mechanics, we know what that should mean. In quantum mechanics, it should mean, just an operator that, if you imagine having some spin chain, some chaotic spin chain, this should be an operator that acts just on a few qubits, okay, on a few spins. And it should not be an extensive operator. I'll get to what we think it means in CFTs in a second. But for now, let's just consider quantum mechanics. So this is a simple operator. Then if O is simple and the theory is chaotic, you have this general structure. Okay, so there's a diagonal piece. And there's a smooth function of the energy that's both theory and operator dependent, which is FO of Ibar. This is the mean energy. And then there's an off-diagonal piece, which is exponentially small in the entropy. There's another smooth function, which is, this is the microcanonical one-point function of the operator. And this is the microcanonical two-point function, or the Fourier transform of the two-point function of the operator. And so F and G are smooth functions, and R and M, the way you often hear people say it, is that this is a random Gaussian variable. With zero mean and unit variance.
As a function of what?
Sorry?
As a function of what?
Oh, as a function of NNM, the energetic states.
So not as a function of energy.
No, these are numbers. So all the energy dependence has been stored here. And these are now numbers that, if you want, range roughly between 0 and 1, and they have, arbitrary phases and they oscillate. And if you sort of average over them, you get something like this.
So you have some continuous approximation to NNM in mind, and does continuous N and M variables, there's some kind of unit mean.
Yes.
Unit variable.
Yeah, that's how we should think about it. Really, the energy levels are discrete, so the arguments that enter in G here are really discrete, not continuous variables. But we imagine taking some, thermodynamic limit where the energy spacing becomes very thin, and there's some kind of continuum limit that emerges. But okay, so these are words that you hear people say, but okay, they're not true for two reasons. The first reason is that these are not random variables. On a definite spit chain, you fix the Hamiltonian, you give me the Hamiltonian. In principle, you can solve for it. If it's not too large, you can just do it numerically. And these are just numbers that are well defined. They're not random. What people really mean when they say random, sometimes maybe we should use the word pseudo-random, is that even if these are well-defined definite numbers, if you start looking at their statistical properties, so RMN is some big matrix, and here's the diagonal, and there's the off diagonals. If you start looking at the statistical properties of all these numbers that appear in lines and columns, they have particular distributional behavior, and that's how we should think about this. Okay, so they're not true random numbers; they're definite, but they have certain statistical properties.
Sorry, I have a stupid question. I cannot read when you say the variance. I mean with
unit variance.
Yeah, that's why I zoomed. Actually, I could barely read that.
Oh, one variance.
Sorry, thanks for bringing me back to the light. So I'll try to write bigger. See, I'm already slipping. Okay, and random and independent. People say that they're independent random Gaussian variables with zero mean.
Sorry, what does one variance mean? Just a stupid question.
Is that if you take all these numbers, RMN, ROP, and you sum over many of them in this matrix or in this table, that you'll get delta NO, delta NP with a 1 here.
Oh, okay. So it's like a Gaussian where sigma is 1, right?
No. Well, okay. This now becomes a convention of what you put in G and what you put in R. People really mean that there should be a 1 here, and if it was a 2,
okay, and 0 is okay. Yeah.
Okay, but this is a bit how you split these two. Really, the way you should think about it is this whole thing is about the variance together. The variance is really a function of the energy given by the 2-point function of this operator, and this whole thing captures it. And now you split it in some way just because you want to put just the number part here, and then you want to have some relation like this with no numbers here. But this is a bit semantics. Yes.
Do you also assume that H is a simple operator, some K-local system, or not necessarily?
I don't think you need that. Well, certainly in the cases where it's been checked, that's the safest thing to do is to make H K-local and then O be a simple operator. If H is not K-local, the notion of simple operator might be a bit fuzzier as well. But I think what's really important basically is that O is approximately a random operator on that, that the change of basis between the eigenbasis of O and that of the Hamiltonian is basically random. Once you have that, you should have a more or less good control over this thing. But it's a good question. I'm not sure exactly how to think about it if H is not killable.
Okay, and then, so this would allow, if you put this kind of operator, it will allow transition between from any energy to any energy with equal probability.
Within the microcanonical window.
I guess I'm a little bit worried that the energies of N and M are very, very different. Taking the average.
No. Very good. This is another great question. So this matrix, should always, here there's energy E, and here there's energy like E plus 1, or, this is within one microcanonical window. And so in the full quantum system, you have many microcanonical windows, and you can ask what happens here, as you sort of ask about correlations of operators through different windows. I think, as far as I know, this is like being studied by condensed matter theorists. They care about this question. I think the lore is that it's even further exponentially suppressed. Then it becomes really exponentially suppressed in the energy. But I don't know how well that's been established. But I think that's the picture. Yeah, great. Okay, and so the first thing that I wanted to say is that these are not random, but for many practical purposes, like computing few point functions of this operator, we can treat them as such. So that maybe we should call them pseudo-random, but they're not actual random. And the second comment is that actually, they're not Gaussian and they're not independent. And people say this because usually the type of observables that they care about is just computing the 2-point function of this operator, for which the Gaussian part of R is enough, and then you don't worry about more. But as soon as you have a non-trivial connected 4-point function, this means that R and M are not Gaussian and they're not independent. Okay, and this is true. I should say that this is true even if you imagine you have now we're back in holography. Imagine you have a theory which is described by free fields propagating on a gravitational background. Even then, using R and M as a Gaussian, using the Gaussian part of the ETH ansatz for R and M does not give you all the Wick contractions of the operators. You get some of them, but not all of them. Okay, so even in a generalized free theory, this is not true. Okay, so this is really important.
In the generalized free theory, this connected 4-point function would be 0.
Yeah, sorry. It depends what you mean by It depends what you mean by connected. There's a sort of an explicit So yes, what I meant by connected, there's an sort of yes. I don't know how to write it, but there's a sort of explicit ordering of the operators that appears if you try to use this ansatz. And the point is that you'll get this Wick contraction and this Wick contraction, but the one that you will not get, or at least you'll get, but with a factor exponentially suppressed in entropy, is this one. And so the only way to get that is to put non-Gaussian elements. I think there's an extremely interesting question, which is because the fact that you get all 3 Wick contractions is required by crossing. There's an extremely interesting question of how to combine ETH and crossing symmetry that hasn't been really attacked too much. I mean, I guess a little bit in this thermal bootstrap paper. Maybe Eric has something to say about this, but I think it's okay. That's an interesting thing to think about. And all of this was worked out in a beautiful paper by Forty and Kircham a few years ago. What they cared the most about was trying to understand how 4-point out-of-time ordered correlators fit into the ETH ansatz. But in the process, they just told us what's the general way to think about this. And the point is that there's going to be non-Gaussianities in the RNMs. So we can talk about the kth moment. We can take this matrix here, we can subtract the Gaussian part and look at what happens for the 3rd moment and then the 4th moment and so on and so forth. And if you look at the kth moment to this pseudo-random variable, it scales in the following way. Okay, so when k is 2, this is just e to the minus s over 2. It's what I wrote here. But there's higher and higher moments. However, so they're there and they're important to get higher point correlation functions right. But they're further suppressed in the entropy. The relative weight of these higher moments in these coefficients here is further and further suppressed in entropy.
Where was this described? What was the reference you mentioned?
Funny and Kirchhoff. I forget the title of the paper, but yeah, it's a really nice paper, and so they worked this out, and it's important to know that even though the relative weight in each of the coefficients is further exponentially suppressed in the entropy, if you look at higher point correlation functions, these effects can build up and give comparable contributions to what you get from the Gaussian part. Okay.
When you say k moments, this is for a single RNN or some contractions of ours?
Very good. Yes, it's for very particular contractions. So, it's for things of this type, and this is what appears in a, it's for what appears in the 4-point function. It's particular cyclic contractions. There's a very interesting question, which is
the same operator, right? You have only one operator that you're using here.
Yeah. Say they're all the same. But if they're different, we would just label the different R by the choice of operator. Each O has its R, and this is like it's like if you have a probability distribution over 4 variables X, Y, Z. And U, this would be like the Pardic moment, X times Y times Z times.
Sorry, but then the trace is running over which indices? Because you said that delta E has to be small, right?
Yeah, so this would be like a microcanonical. So all of these J's here should be sort of projected to the microcanonical window.
No, but sorry, you are summing over repeated indices or not?
No.
You are not summing.
I'm not summing.
The J, K.
This is just saying which of the. So this is saying which of the R's. So eventually, when you compute the 4-point function, there will be an entropy factor coming from the sum here, and that's how these things get.
I was just wondering if these repeated indices would be
no,
sum, then this would.
This is not a sum. In this expression, this is not a sum.
Okay.
And then when you compute the 4-point function, you use this. That will this time involve a sum, and you just multiply it by e to the s. That's what the sum gives you.
No, but okay, but then this is what I'm worried about, because you're taking the average before doing the sum.
Yes. Well.
But when you're doing the sum, you are you have to sum over all energies, and some of them will lead to some very large delta E. So there's some order of limits here that you're doing implicitly.
Sorry, are you worried about when you insert a complete set of states here? You're worried about the energies that are not in the same microcanonical window?
Yeah, exactly. Yes.
Yeah, so I think this goes back to the question that was asked before of, what are the contributions that are further suppressed? That are, outside the microcanonical window. And the idea is that, again, I don't know how well this has been established, but the idea is that those are even more suppressed. They're like exponentially suppressed in the energy.
But certainly for very low energies, these will be coefficients of order 1, right?
Not necessarily. So here, remember here, there's a heavy operator, right?
Sorry.
Right.
Okay.
This is like
this is inserted on.
This is thermal.
Okay.
So then so yes, everything contributes, but you have to keep track of what's the dominant piece is, and the dominant piece is really when all of them are in the microcanonical window. Up to other corrections that again I don't know how well they're controlled. Good. How am I doing with time? Not well, probably.
Not so well, especially if you start the. Yeah, you have about 10 minutes.
Yeah. Okay. I'll just say I'll. It's fine. I won't get to everything, but that was okay. It was meant to be open-ended and see where the discussion goes. So that's the statement about ETH in quantum mechanics. And now you can ask how to think about it in conformal field theories. And in conformal field theories, there's a couple of different things to keep into mind. The first one is that in conformal field theories, you have primaries and descendants. And it's very easy to convince yourself that this cannot be a statement that's true for all energy eigenstates. Because if you just take, primary, or whatever, and there's a diagonal piece, and then you change this to make it just one descendant of the same primary, then it's going to be much bigger than this. Okay, so the first thing that you need to do, and this is not a big deal, is just you have to go from all these primary ETH is meant to hold only for primary operators. This gets more intricate in 2D CFTs because now you know what a descendant is becomes much more complicated because of zero-zero symmetry. But again, just one should restrict. This should be really thought to be a statement about in 2D zero-zero primaries, and in higher dimensions just primary operators.
Stupid question.
Yeah.
Sorry, it's just, is it clear that energy eigenstates and primaries are the same? Can I have, at zero temperature, okay, I can get primaries, but if I am at finite temperature, how do I know that energy eigenstates are going to be primaries? It's just a stupid question. Maybe it's obvious, but.
This is not about, if I just hand you an energy eigenstate, it might be not completely trivial to see, but the idea is just I'm saying this ETH ansatz, you should organize it for the primary operators. And then think that the ones for the descendants are fixed by conformal symmetry and just. Yes,
but the question is, how do you know that that an energy eigenstate will be a primary? That in general, because normally if I have some states, the moment if I start mixing them, I'm going to get some huge superposition of a huge amount of states. How do I know that if I have an energy eigenstate, it will not be the primary of some operator and the descendant of another operator mixed up with with a huge mess? How do I know that it will still be a primary?
Yeah, the temperature doesn't change the argument. You have to just diagonalize the Hamiltonian and you pick your basis. Maybe the question that you're asking is if you're at high energies and I hand you an energy eigenstate, is it typically going to be a primary or not?
Yes.
And the answer to that, well, that depends now on 2D CFTs or higher dimensions. In higher dimensions, the argument is that yes, a typical operator is a primary. In 2D CFTs, the answer is no, a typical operator is not a primary. It's a zero-zero descendant, but its energy is mostly made out of the primary energy. So it's a bit, we can maybe come back to this at the end. I do want to say something new. For now, this has been a long review, I guess. But the idea is that, if you look at a typical energy, it's going to be the primary part plus some level descendant from zero. And the point is that delta P is much greater than N for a typical operator. So it's not true that a typical operator is a primary, but it's mostly made out of a primary part and has a few descendants.
Does this work in minimal models? Because
of null states?
No, because I have a few primaries.
Yeah. None of this works in minimal models, right? Minimal models is precisely cases where this does not apply.
It's not good.
Because those are integrable, rational. Okay. So that's the opposite end of the spectrum where we should not go. Okay. And then the spectral form factor for minimal models is super regular and just periodic with like an order 1 period. Sure. And according to what we agree will be our definition for today, that's not a chaotic CFT. Good. Okay. So that's what you need to keep in mind. And then the statement that EN O EM, well, in CFTs you can use the state operator correspondence. So this is just a 3-point function of operator, in other words, an ODE coefficient. And so ETH in CFTs becomes a statement about OPE coefficients, what the statistical distribution of OPE coefficients is. And in particular, not all of these 3 operators are born equal. Remember, O needed to be a simple operator, and EN and EM were going to infinity in the thermodynamic limit. So this OPE coefficient is really an OPE coefficient between a light operator and then 2 heavy operators. Okay? So that's what ETH is telling us about. It's what is the statistical distribution of OPE coefficients of this type. Okay, but once I start asking this question, then it seems like I'm allowed to ask other questions, and I can pick various other types of OPE coefficients. And sort of the most interesting ones, so we just said that this is what ETH is telling us about, but you can ask what happens to these types of OPE coefficients. Okay, where there's either 1 or 3 heavy operators. And so in this paper with Jan from a bit more than a year ago now, well, we defined an ansatz, or we proposed an ansatz called the OP randomness hypothesis, that saying that all of these are random. Or I just said we shouldn't call them random. All of these are pseudo-random. Okay, and the intuition behind it is kind of the same, is that heavy operators are very complicated, and if you don't know what they are, you might as well treat them as random, with a probability distribution, which the leading order is Gaussian.
So by,
Yes.
by AV, I guess here you mean some kind of typical AV operator. They cannot be arbitrarily complex
Oh yeah, no, heavy can be arbitrarily complex, but it needs to be heavy. So it's important that in all of these formulas, delta H goes to infinity. So it's in the thermodynamic from it.
But not in a fine-tuned form, no, because if I don't see how you could have any kind of ETH formula if the AV operator was really checking something extremely subtle and precise about the system.
You're asking,
at all
yeah,
scales.
if you put a heavy operator here and ask now, so this looks like now this, from the ETH point of view, this could be like a microscopic operator that probes the fine details, right? Well, okay, good. So that's what I wanted to talk about, and what I'll do in the last 5 minutes I have is what we
Andrea asked me to be kind with you because you had 30 minutes of questions. So
okay.
you have time.
Thank you, Andrea. But we have to change the whole setup for the next talk. So that I think that's a hard cutoff on how far we can push.
It's not so hard. It's not so hard.
Good.
Is delta H is n squared or it's really?
So it's really infinity. So okay, it's not literally infinity, but it's bigger than any other parameter in the problem. Yeah. Or CT or C, I don't know how you want to call it, but yeah, it's really in the thermodynamic limit. So the usual thermodynamic limit. Good. Okay, and so so that's the proposition. And now the question is, okay, it's great to make conjectures, but how do you prove them, or at least show some evidence? You can ask the same question about ETH, and ETH is not proven. What you can do in ETH is just take your favorite quantum mechanics and do numerics and check for this. And this has been done by a lot of people, and it seems to work in you take a chaotic spin chain, or people have checked it in the XYK model. All of that seems to work. We can't do it in CFDs yet, so hopefully one day the bootstrap will be powerful enough to probe things like this. Let's hope. But for now we can't. So you can't do numerics to check whether this is true or not. So what can you do? And the best thing that we know how to do is to look at consistency checks. And as I just explained to you for ETH, and this is what Fanny and Kirchan worked out, is that what's important in ETH is not that the distribution is exactly Gaussian. What's important is that to leading order it's Gaussian, and it's corrected by higher moments which are expressed in the entropy. Okay, that's really what's important. And so you can ask, can we check this? The fact that to leading order it's a Gaussian. Can we check that the non-Gaussianities are further suppressed in the entropy? And so the answer is yes, and that's what we're doing right now in this paper that hopefully will come out next week. But I should first say something. I should first say a little bit more about these things. It turns out that these things in CFTs, the Gaussian part is fixed, and actually many of the higher moments are highly constrained by crossing symmetry. And this is known as asymptotic formulas. And the idea for it is very simple. Imagine 4 operators. Okay, and go to a limit where these 2 operators are approaching one another. Then the leading contribution is the identity operator. Okay. But by crossing symmetry, this has to be equal to an infinite sum over many other operators in the cross channel H. Right? I'm just writing the crossing equation, and I'm going to a limit where only the identity contributes here. And by exploiting this, so this was first done in a paper by Slava et al. Many years ago, and they were really worried about OPE convergence at the time. But exploiting this, what you can do is you can write down a formula. Should put O here. You can write down an asymptotic formula for the OPE coefficients squared. And you figure out that formula by plugging it in here such that you reproduce the pole of the identity. Okay, but what is this thing? This is nothing but the Gaussian part of this thing here, right? And so this is not a check of ETH because we're not, computing the individual coefficients and checking whether or of the OP randomness hypothesis. We're not computing the individual coefficients and checking if they satisfy this pseudo-random ansatz. But what we're doing is saying, well, actually, the thing that we see here is that the Gaussian part of the distribution is fixed by crossing symmetry. Yes, what's your...
So in this consistency test, the dimensions of the O's can be anything, the lighter heavy, but the H is like
Yeah. So O could be made anything here, but it has to be fixed, whereas this one is really going to infinity, because how heavy this needs to be depends on how strongly you're projecting to the identity operator. But it's really, this is an infinite sum over all conformal dimensions, but it's dominated at very, very, very high energies. And at energies that are fixed by the cross ratio that you're speaking here, roughly speaking.
Alex?
Yeah.
Just to clarify your ansatz,
Yeah.
You're mainly making a statement about what would be the subleading term in the ETH language, right?
Yeah, very good. No, thanks a lot. That's really important. Yeah, so for this guy here, there was a diagonal piece and an off-diagonal piece, right? And there was a diagonal, for this guy here, and there was a diagonal piece because, H and H prime can be the same, you can contract them together. Here, because we have an odd number of heavy operators, there is no diagonal piece. And so all there is left is this, exponentially suppressed decaying part, basically.
And yes, good. So my question was, is the exponential suppression part of your ansatz?
No. No. I would say no. We think it's related to the entropy, but is it S over 2, S over 4, S over 3? Is it S times some weird fractional numbers? That in principle, we don't know. I think we would be happy with anything. And that might be theory dependent. And it turns out that it is, because so this statement for D greater than 2, it turns out that the exponential suppression is e to the minus S over 2, just roughly speaking, because there's two operators here, right? So COOH was like e to the minus S over 2, because there's two of them and there's e to the S states, and that's how you get this. But if you do it for 2D CFTs and talk about zeros or primaries, it becomes e to the minus S over 4. So, okay, the statement is that, there is some suppression in the entropy that's organizing the system, but how much it's suppressed by, we don't know. It might be theory dependent.
What about the heavy? What's your ansatz there?
So the heavy, so the idea is that, let me write it on the other side. I'm out of time, right? I'm already over.
Well, with 5 minutes more, you have still 5 minutes.
Andrea told me I had a half hour. It's okay. I'll take
then we're in trouble.
I'll take 5 minutes, and here I'm going to just write some more precise formula. So the ansatz for the heavy operators is that I don't know, M and L, and all of them here are meant to be heavy, right? Is that this is just some random variable times, I don't know, before I had F and G, so H of E and the various delta E's. Okay, so there's no diagonal part, everything, and this is going to be suppressed in some way in the entropy. Okay, this is a random variable with the leading order Gaussian distribution. And so if you want, from the ETH perspective, I'm regrouping this e to the minus S over 2 and this G together in what I'm calling here H. Okay, it turns out that we know what this thing is because there's a similar trick that you can play, at least for 2D CFTs, there's a similar trick to this that you can play. And the idea is to exploit genus 2 modular invariance. And just like, at genus 1, that's how we derive the Cardi formula, which is also an asymptotic density, but not of OP coefficients of states. The idea is that if you do the same trick as Cardi at genus 2, you go to one channel, you keep the identity, just like here, and then ask what it means in the cross channel, you get an asymptotic formula for C heavy, heavy, heavy. Okay, this was done in 2 papers by Maloney et al. And there's a nice expression, and you can check that it scales as e to the minus 3s over 2. Okay, and I'm already over time, so I don't want to go on for too long, but one of the important things to check that this is true is to verify that the higher moments are further suppressed in the entropy. And we were actually able to do this by exploiting genus G modular invariance. So you can play the same trick at higher genus. And in general, if you go to higher genus, it's going to involve more and more OBE coefficient with some particular index structure. And you can do that. So I'll just write down the results and then I'll stop, and I won't really say anything about wormholes, but you can ask me. So if you look at the kth moment of this thing, and you have to say how the index structure are contracted. So we define two structures that make sense at arbitrary genus, and something that we call the skyline channel, which at genus 3 looks like this, and at higher genus it looks like the New York skyline. It looks like this. So this behaves in the following way. Now these are these coefficients that you need to get right. So here you have to heavily exploit Virasoro symmetry, but you can get an expression for them. And you see that this should ring a bell and look very much like this k minus 1 over k, right? Things are further suppressed in the entropy. The numbers that come out here, okay, we couldn't guess them from first principles. Maybe this is also related to what you're asking. You have to use Virasoro symmetry and you get something like this. But what you can see is that the higher moments are further suppressed.
So sorry, to try to understand more, you use the assumption of ZTH, and that's on the HHO and genus 2 modular invariance to get that, I guess. You need to also relate it to the other one?
Yeah, so really what we derive here is an asymptotic formula of this type.
But it would not be true in minimal model, for example. So I guess you have to relate it to something exactly. Somewhere.
So that's an excellent point. So the asymptotic formula is true in all theories. So really here, for these results, you require C greater than 1. But say the theory had, I don't know, extended chiral algebra, then maybe it would still be rational, but these formulas would be true. But the important point is that, yes, so you're not testing ETH here because, this will be true even in a rational CFT. But what you're testing is, how could I say this? If you want, this formula is always true, but how it's realized depends strongly on the theory. In a minimal model, what's going to happen is that this formula will still be true on average, but it's because some contributions are huge and others are 0, because there's like selection rules. That's what's going to happen in a rational theory. And in a rational theory, it's going to be spread out sort of much more evenly around all the operators. So that's why this is not a test of ETH, because it's true even in rational theories, but it's a consistency condition to at least show that something like this is possible. Then to really prove it, you indeed need to go look and see whether the individual coefficients are all contributing to this, or whether some contributions are huge and others are small. But that's again that is encoded somehow in the higher moments. Right, so
also it's a sum of positives, so none of them can be big, right?
Here, yes, not here.
Okay.
Here, the contractions are such that it's not a manifest sum over positives, but indeed you're right here. Yeah.
If you say equals 2 with this formula, you will get the previous ones because you have different contractions. Or
yes, I didn't. So it doesn't work. Yeah. If it doesn't work for this one, it's because indeed this thing might degenerate to not to. So this is yeah. So this is a formula in maybe not the equivalent of what the skyline channel becomes at genus 2. Even at genus 2, there's another formula that you can write at genus 2, which is something like this, a different contraction. And I think maybe this one reduces to that in this limit. That's why. Yeah, thanks. That's a good question. And okay, so we can derive other formulas of this type. We can also have the kth moment in the COM channel. COM channel looks like this. And it has, an arbitrary number of lines here. And again, again, you get different numbers here that we couldn't have guessed from first principles, but it's further suppressed in entropy. Okay, so it seems that, this general structure that should also be there in ETH seems to also apply for these things to the level that we can check. Okay, and then there's a lot more things. So I'm out of time. I'm not going to go on. There's more things that you can do. You can use you can use intuition from random matrix theory to try to to show something like this by thinking about C as a linear operator on a triple Hilbert space. So there's a bit more evidence that we're gathering that this conjecture is true. But yeah, let me just stop here. And so thank you for your attention. That's me about work.
Thank you. Do we have questions?
I have a question. Can you comment on the subleading terms in the LLH case?
I can, yeah. So this is also something that we looked at. So this is also probing higher moments of C heavy, 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 but in a different way. So here's something you can do in all dimensions, and then you can do much more fancy things. You can do much more fancy things in 2 dimensions, because there we can also get the arbitrary kth moment, but we don't know how to do that in higher dimensions. But this is sort of the generalization of what Slava did, like Richkoff or Tazzi et al. From many years ago to the 6-point function. So consider this in the OP limit where these pairs of operators get contracted together. You keep only the identity. And now you ask, how is that reproduced in the cross channel? Where, you know, 3 heavy operators do. Right? And you can ask what needs to be true about this such that it matches the identity contribution here. And this gives you an asymptotic formula for C light, light, heavy, C heavy, heavy, heavy. So it's also like a quartic moment, but this time it's a mixed one involving both heavy, heavy, heavy and light, light, heavy. And we can derive an asymptotic formula for this thing. And this is actually pretty exciting because this works in any dimension. So you can make it very nice in 2D thanks to Berezov's symmetry, but you can also do it in higher dimensions. For at least in the same way that Richkoff and all did it, when you do it for all operators. Doing it for just primaries requires the 6-point blocks, and we're working on it, but that's hard. But at least for all operators, you can do this. And then you can probe something about C heavy, heavy, and D greater than 2, which for now we don't really know anything about.
If I would just care about the LLH, don't I get something from the 5-point function?
Yeah, we haven't. Probably, yeah.
Oh, because you said you have some ETH type ansatz for S LL prime H.
Yeah.
But you just told us about the Gaussian part. So my question was, what about the sub?
Yeah, but this is already non-Gaussian, right? This has 3 of them. But you're saying there's something
easier.
easier.
Something new, so.
Yeah. So yeah, there's probably something you can do with the 5-point function. It depends in which channel you want to look at it, but I'm sure there's something that can be done. We didn't really study that in much detail. We were most excited about trying to probe something about this in higher dimensions because, you know, there's no equivalent of a genus 2 surface, a genus 2 partition function that probes this in higher dimensions. Yeah.
Other questions? Yes.
Can you say the punchline about the 1 point on the factorization?
Yeah, okay, so the thank you.
Is it true that we did not hear of them after?
Yeah, so I didn't say anything about wormholes. The idea is that what also gave us further justification for the OP randomness hypothesis is that if you take this hypothesis and treat the OP coefficient statistically and then compute the square of a partition function using this ansatz, you can match the genus 2 wormhole. So there's a wormhole that looks like this. I guess this was one of the questions from the virtual world, is that there's a wormhole in 3D gravity that looks like this. And you can match its on-shell action, which turns out to vanish, by keeping just the Gaussian part of the OP randomness hypothesis. Okay? So this was the wormhole that was first studied in Miles and Malacena, and that they were very confused about. So the picture seems to be that in gravity, if you think that what semi-classical gravity does is that it doesn't do microscopic CFT computations where you would obviously not have this and things would factorize, but it computes things, you know, statistically. We already know that from black hole thermodynamics at the beginning, you know, it computes the coarse grain entropy off of all of the energy eigenstates. And here the idea is that it computes coarse grain correlations among the microscopic OP coefficients. And because it's coarse grain, you have wormholes. It's not the actual microscopic information. And you can ask how the higher moment story affects something like this. And the statement is that now if you look at the quartic terms, so you have these quartic terms from, say, the genus 3 partition function, and they do influence potentially how you should think about what this thing is. And so the idea is that this thing is not always just the Gaussian part. It can be, it's really sort of like the wrong Wick contraction in the Gaussian part plus the quartic term from genus 3. And okay, there's even a longer story there where we seem to find a contribution in certain, in this other channel that Boris was asking about. If you look at this channel, and you look at what the quartic potential does for this channel, for the square of this, we even seem to find a new contribution that's bigger than the wormhole. It requires you to have matter in ADS. It requires, in pure gravity would not be there, but it seems like there's new, like this, you know, this OP randomness hypothesis makes a prediction for new connected solutions in 3D gravity with matter that we haven't found. So. Okay, thanks. That's a 1-minute summary of the wormhole story.
Other questions? Otherwise, there is a question from Stan in the chat. He's saying that ETH does not only imply that RMN are Gaussian distributed, but also that the phases are uniformly distributed. And he's asking how this carries over for CFTs. If I'm not.
Can I ask the question out loud?
Yes, sure. Yeah.
So I just wanted to recall that the ETH makes two statements. One is that the amplitude of the coefficient of the exponential that's exponentially suppressed with the entropy is from a Gaussian distribution, although it may be non-Gaussian, but also that the phase of this coefficient is uniformly distributed. So there are two points in the ETH. So I was just wondering, when we look at the CFDs or higher CFDs or more complicated theories, what happens to the statement that the phases are uniform distributed. So I just was wondering whether it has some implications about the scattering phase shifts.
Yeah, thanks. That's a great question. The honest answer is I haven't thought too much about it. What I would say is that whatever applies in ETH should also apply for high dimensional CFT and higher moments of OBE coefficients, with the only extra constraint that, you know, you have to be careful what unitarity fixes. Like, you know, if there's realness properties of the OBE coefficients, you have to take those into account. But other than that, I'd say that it should work more or less the same way as what you're used to in the usual ETH ansatz. But I haven't thought about it too much. It's a good point.
Okay, thanks.
Okay, thank you. So I think it's time for the break.